Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the second lecture of week 5 where we are starting right away from where we left. In the previous session we had discussed the concept of flux density and the fundamental experiment where it actually originated from. That was the Michael Faraday's experiment, and we discussed the concept of flux density, and at the very end we realized that if a point charge is placed at origin of a spherical coordinate system, so the flux density for that case is given by this formula. And here in this formula, which we had already derived or discussed in chapter 2, we said that for that particular charge arrangement where a point charge is placed at origin of a spherical coordinate system, the electric flux and electric field intensity is given by this expression. So observing these two expressions, we said that electric flux density and electric field intensity are actually related to each other using this expression, and we tried to try to give you an intuitive example to understand the difference between flux density and field intensity, and why flux density is independent of the material while the field intensity definitely depends on the material itself. So this was the expression, the final take-home expression, and I said that this expression, although derived from a special case, but it is not a special relationship, rather it's a generic relationship between electric flux density and electric field intensity, or in other words between D and E. And that fact was elaborated by an intuitive example which I gave you at the very end of the previous lecture. So now moving on, keeping this expression in mind, and that this expression, this relationship is generic, let's see how many types of source distribution we saw and which are actually possible in nature. So there is a possibility of charge arrangement in the form of zero dimension, so meaning in the form of point charges, or the source can be arranged in one-dimensional infinite line charge fashion, or it can be in two-dimensional charge arrangement, which is infinite sheet of charges, which is given by surface charge density, or three-dimensional finite volume charge density. Obviously this cannot be infinite. It means if it would be infinite, it means that the universe is filled with charges. In that case finding out the intensity would be impossible. So for each case we had derived in the previous chapter the formula for electric field intensity, the first type of vector field effect. Now we want to find out the second type of vector field effect for all the four possible charges. इसके अलावा कोई और ऑप्शन मुमकिन ही नहीं है चार्ज अरेंजमेंट का. चार्ज अरेंजमेंट का can be among these four, one of these four fashions. Okay, so having said that and keeping this formula in mind, now we can fill this table. For a point charge or n point charges, the total flux density can be found out using this formula, except that there should not be any epsilon naught here. So now this formula is going to give us electric flux density for n zeroth dimensional charge distributions. As simple as that. Just remove epsilon making use of this expression. For an infinite line charge density, if you want to find out the flux density surrounding an infinite line charge, what you need to do is carry out this expression. That's it. Compare these two. Only epsilon naught is absent here. As simple as that. So electric flux density for a two-dimensional charge distribution infinite sheet is given by rho s upon 2 an, as simple as that. For a finite volume charge distribution, electric flux density is given by this expression. Okay, so they should be square. So you can see from here that how much powerful is this expression. Very powerful expression. So whatever we had discussed in one chapter for electric field intensity, we have discussed the same, corresponding same for electric flux density, and just one topic, knowing that this relationship is true, and it's a very powerful relationship. Okay, so there we go. Electric flux density of every possible charge arrangement is there. Okay, so now after discovering the formula for electric flux density for all the possible charge arrangements, let's move on to the next topic of this chapter, which is Gauss's law. I said that these topics, Gauss's law, electric flux density and divergence, they are very closely related to each other. So I don't want to start this topic randomly. Okay, I just want to connect it with Michael Faraday's experiment, and this was Michael Faraday's experiment: inner sphere, outer sphere, positively charged or any charge. I'm taking this as a positive charge, inner sphere. Same amount of charge is appearing on the outer sphere, but with of opposite nature. If this one is positive, this one negative, that one positive. Nevertheless, the amount of charge would be the same. And for this arrangement, we had discovered that the formula for electric flux density is given by this, or there is an error here. Sorry. So this there should not be any epsilon naught here. So it's correct now. So after that, what we did, we said that okay, if we take a sphere in between these two spheres actually this formula came out for the flux density of that imaginary sphere. Okay, so there is one implicit implicit assumption here, that the flux, this line is flux line. Okay, I have shown only 8 lines does not mean that only there will be 8 flux lines. There will be infinite flux lines emerging from the inner sphere and reaching at the outer sphere, but we have shown only 8. हर जहत में, हर डायमेंशन में, हर डायरेक्शन में जो फ्लक्स जा सकता है हम वो दिखा सकते हैं as simple as possible. तो हम 8 डायरेक्शंस में दिखाते हैं. This is a common practice. Okay, so we always show the flux in 8 directions, although it is implicit that there are infinite lines here. So from each and every place the flux line will be passing, but for the sake of simplicity and clarity, we just show the directions on 8 lines, by 8 lines or in 8 directions. Okay, so there is one thing implicit in this whole scenario which we discussed in the last section, that the flux which was leaving the inner sphere was perpendicular everywhere to the sphere, because the direction of flux is AR, and AR is always perpendicular to the sphere. And also this flux is perpendicular to the outer sphere. It means that the charge distribution is so arranged in this particular experiment, the charge distribution is so arranged that the flux is always perpendicular to the charge distribution. Okay, just consider that there is no material, only a sphere of charges, a hollow sphere of charges is present here, and even in that case also the flux leaving that hollow sphere of charges would be perpendicular to the charge everywhere. Okay, and wherever this flux would terminate, there will be a negative charge everywhere on that sphere. Okay, so the implicit assumption in this whole experimental setup was that flux was everywhere perpendicular to, or the flux or the charge was so arranged that the flux or the effect was perpendicular to the source itself everywhere. In that case, we realized that the formula for electric flux density is this, but this might not be the case every time. The charge distribution can be random. It may not be in the form of a hollow sphere, or the charge may not reside on the surface of the metallic sphere, or the charge cannot always be a point charge. It can be arranged in any fashion. It does not matter actually in which fashion the charge is arranged. The total flux which would reach, okay, the outer sphere, or the total flux which would cross this imaginary sphere of radius r, the total flux will always be the same, because the Michael Faraday's experiment said or showed that the total flux was proportional to the charge. So it does not matter whether the charge is in a symmetric form or it is dispersed something like this and in a random fashion. Charge, as long as the amount of charge is same, the flux crossing a particular surface would be the same. So this is what we concluded in the last session. So what is the contribution of Gauss's law? Gauss's law says that electric flux passing through any closed surface is equal to the total charge enclosed by a surface, exactly what we had discussed in the previous session under the Michael Faraday's experiment, and this is exactly what we discussed in the previous session while we had not even introduced Gauss's law except in the title of the chapter. That's it. So this is exactly what Gauss's law is saying. चोर कहीं का वही काम जो उसने कहा था माइकल फैराडे ने, वही इसने कर दिया. So what's the contribution of Gauss's law? The contribution of Gauss's law is that the Gauss's law removed that implicit assumption which was there in the case of Michael Faraday's experiment, that the source was so arranged that the flux leaving the source was always perpendicular, was everywhere perpendicular to that source. Gauss showed that Gauss was not a physicist. Gauss was an excellent mathematician. So he showed that the source if the source is not so symmetrically arranged, like in this fashion, if the source is arranged in this fashion, and the source is not so symmetrically arranged that the flux can be regarded as perpendicular to the source everywhere, then in that case what would happen? In that case, how we can find flux density? So that's a very big contribution. So not only that, if he generalized that Michael Faraday's results so much that he said that not only the charge can be arranged in any arbitrary fashion, if you want to find the flux crossing any arbitrary shaped closed surface, the emphasis is on closed surface, any arbitrary shaped closed surface. So how to find the total flux which is crossing through that arbitrary closed surface? In this case, the green surface, or the surface with radius r, was also so symmetric that the flux was everywhere perpendicular. And in this case, now what the contribution of Gauss was that he showed that how to find flux density if neither the source nor the surface on which you want to find the flux density are so symmetric. They are totally irrelevant to each other. They are independently arranged in their own fashion. Then how to find flux crossing through any arbitrary shaped closed surface. Okay, so उसने क्या किया, अंदर वाली चार्ज अरेंजमेंट को भी बिगाड़ दिया, आर्बिट्ररी कर दिया, और आउटर सरफेस जहाँ से फ्लक्स की डेंसिटी निकालनी थी, जो माइकल फैराडे के एक्सपेरिमेंट को डिस्कस करते हुए बहुत सिमेट्रिक थी, उसको भी चेंज कर दिया, उसको भी ऐसे आर्बिट्ररी बना दिया कि इन दोनों का आपस में कोई ताल्लुक ही ना आ रहा है. तो ही मेड श्योर दैट द फ्लक्स व्हिच वुड लीव दिस चार्ज would cross arbitrarily through this closed surface. And now figure out what is the contribution of how to calculate the flux density. So when we were discussing this, if we had this symmetric case, if we had chosen any arbitrary a surface area, differential area, let me just remove this green sphere and just consider the outer sphere, so that discussion will be valid for any sphere within these two spheres. So let's take a differential surface area on the outer surface. So if I want to consider the flux crossing the surface area, that flux will be in this direction, and that flux must have originated somewhere from the corresponding patch on the inner surface area, inner sphere. So from here the flux must have reached the outer surface, and let's say this outer surface is not metallic, it's an imaginary surface. So this flux will cross this external patch just like this. Okay, and since flux is everywhere perpendicular to the surface, so this patch, which can be given by differential surface ds, and the amount of flux which is crossing through this differential patch, that is, let's say, is given by d psi. In that case, definitely d psi divided by ds will be what? Will be flux density. Okay, flux density. So to define flux density such that there is in this fashion, there is one implicit assumption that flux is everywhere perpendicular to the surface, or in other words, the direction of the surface, which we all know is always taken as the perpendicular of at the surface. So direction of this green patch is perpendicular to this green patch and is always pointing outward of the volume. So it should point in a direction which points outward of this whole volume. So the direction of this flux, which is the green arrow, and the direction of this patch, which is the black arrow, both are the same. Okay, this direction of the patch is perpendicular to the patch, the direction of flux is perpendicular to the patch. So it means that direction of flux and direction of patch were parallel, or in other words, flux was perpendicular to the surface, but flux was parallel to the direction of the surface. Okay, so since direction is perpendicular to the surface itself, so flux is parallel to the direction of the surface. So if it is so, only then we can define flux density as this. This is how we simply divided the flux, divided by the surface area. But if we take the general case in which this possibility may not be there, so in that case, let's say we take a patch here. Okay, and the direction of this patch is definitely perpendicular to this patch. This is the direction of the patch ds, or let's say this surface area is incremental. Okay, so in this case, flux is, em- emanating from this source in a random fashion, okay, from everywhere. And let's say, for the sake of generality, and it appears also just like this here, it appears so here that flux, let me draw it in green, and I hope you could see it in green. Let's say the flux which is passing through this patch, this is the amount of flux which is passing through this surface area, differential surface area, or incremental surface area. Okay, and there is an angle, let's say theta, between the direction of the surface and some direction of the flux. In that case, we would only be able to define the flux density, magnitude of flux density, in this case, if we would somehow find the component of flux which is perpendicular to perpendicular to that patch. So a point just struck me, which is a generic confusion among students, and this is perhaps because students have been taught in this fashion in their pre-engineering, that these lines, that the flux is what? Flux is number of these lines, okay, or flux density is what? Number of these lines divided by certain unit area. So this is not true, because flux is not the number of lines. Why? Because as I just said, the flux which will be emanating from the inner sphere and reaching the outer sphere would be there would be infinite number of lines. So we just for the sake of clarity, we just showed 8 lines. So flux is not this line, this line, or this line, or this line. Flux is something not that definite. The flux area or the flux density is not number of these lines divided by area. That would, considering it in this fashion, is also wrong. Why? Because there are, if I would try to actually draw the situation, I won't be able to do that, because in that case I'll have to draw infinite number of lines. So infinite number of line divided by some finite area will definitely give you an infinity. So if we consider that to be true, that flux is number of lines per unit area, then in that case you would get always an infinity. Flux lines per unit area is not flux density. Flux density is flux per unit area. And what is flux? Flux is a scalar quantity which is equal to the charge enclosed by a certain closed surface. So what I would say, why this point came to my mind is the fact that I just unintentionally wrote something here, which is actually I should not have written it over here. This is not the differential amount of flux leaving this patch, rather this is the flux density, okay, flux density vector, because direction is always associated with flux density, not the flux, because flux is something which is scalar. It is simply equal to the charge enclosed by a certain charge enclosed by a certain surface. And since that surface happened to be, in this case in Michael Faraday's experiment, since that surface happened to be perpendicular to the flux everywhere, in that case we got this formula. In that particular case we got this formula. Okay, so remember that flux itself is a scalar quantity. It moves from one point to another point. So just to show that, we draw arrows. Okay, it is not necessary it moves in this fashion. It may move in any random fashion, but we say that it is moving in this fashion because we don't know anything about it, and we have not been proven wrong so far, considering flux to be following these straight lines. As long as we are not proven wrong, we would consider everything to be correct. This is the beauty of science. Okay, so actually the green arrow, which is which I just showed here, is not flux, it is flux density. Okay, which would be equals to this flux density ds, just to show that the flux density over this arbitrary surface ds is equals to, the magnitude is equals to the amount of flux crossing through this differential patch divided by surface area, just like this. Here we considered differential areas. Here we have considered incremental areas. कोई मसला नहीं है. As soon as we apply the limit delta s tends to 0, this delta psi will become d psi. It does not matter whether we consider the differential definition or incremental definition. These two will be same if and only if flux is in such a direction, flux is moving in such, is pointing in such a direction, is moving in such a direction, or is moving in such a fashion that flux is perpendicular everywhere to this surface, or the flux is parallel to direction of the surface. If this is so, then delta psi upon delta s or d psi over ds both are the same, because average value would remain the same. So if this is the case, this is that surface area delta s, and the flux crossing it perpendicularly is given by delta psi, then this expression is true. But what happens if this things comes? So if I remove this d, now this is equals to this, and these two cases are valid for this particular scenario where flux is leaving the area perpendicularly. So the word leaving is important, isn't it? What we are trying to do, we are trying to find, using Gauss's law, we are trying to find electric flux passing through or electric flux leaving, or chalo passing through a certain cross-sectional area. So something which would pass through some other thing means that we are interested in the perpendicular component only. So for that, let's consider an example. Let's say you are watching from some height, and this is a wall, okay, coming out of the board, and this is the wall, and there is some opening in that wall. कोई दरवाजा था जो आपने यहाँ से हटा दिया, and let's say wind is blowing through in this direction, okay, in this direction. So how much wind will cross this wall would be depending on the size of this opening. Not only that, but also the direction of the wind, isn't it? Let's say from the left hand side we have got only 3 lines, 4 wind flux lines coming. So if that the direction of the wind flux is exactly perpendicular to the surface, so whole of the flux will leave just like this. So if I would ask you in this case, give me the wind flux density, magnitude of that, you will say that, okay, count the wind flux, whatever the flux we have, and then divide it by this area of the opening. This is what you would say, and this is what we are saying here. But let's say if wind would not blow in this fashion, rather wind is blowing in this direction. Now definitely the wind which would come out of this opening would be smaller. So it means that it is not only the opening or the surface area in the wall which would decide the amount of flux, the amount of wind flux leaving this wall. Rather, the direction of the wind blowing would also affect. This would also affect the amount of wind flux coming out. So this direction of the wind can be given by some vector quantity, which is which may be the wind velocity. And if you want to find out the amount of wind coming out, you have to take care of both things, because a particular component of this wind which will be parallel to this wall will not cross this wall. Rather this component of wind which is perpendicular to the wall, this component will cross. All right. So let's say if in the previous case when wind was blowing in this direction, the velocity was the same as this one, the speed of the wind is same as this one. Direction has been changed although, but let's say speed was the same. Okay, speed was the same in this case as it was previously. The amount of wind flux leaving, or the wind leaving of if a person is standing here, he would definitely experience a different amount of wind here in this case as compared to the case in which the wind was flowing perpendicular to the wall. Okay, so in this case when the wind is making some angle with respect to this wall, definitely we can resolve this direction into two components, a component which is perpendicular to the wall and a component which is parallel to the wall. And we would say that this component is not actually crossing the wall, rather this component is making a portion of the wind to blow or to flow parallel to the wall. So this component will be flowing in this direction. And if someone is standing here now, he would feel some wind now. In the previous case when the wind was perfectly perpendicular to the wall, in that case whatever the wind was coming from the left would go, so only this person would experience some wind, and this person would experience total hubs. Okay, no wind at all. Okay, so but in this case this person will obviously experience some wind, and this person will obviously experience some wind which is smaller than the previous case, as long as I am considering that the speed is same. Velocity is different now because the direction has been changed. So actually what component of this wind is now making this person feel the wind is this component which I just crossed, because this component is flowing perpendicular to this wall. I think I made myself clear. Okay, so if this is the case, then we won't represent it by d, we would represent it by ds. Okay, now for flux density over this patch, in which the direction of flux density or this green arrow is not same as the direction of the patch, we have to make some amendments here. Why? Because we this thing will not give us ds, rather it should give us ds, the normal component. समझ में आती है बात? If you use this relationship, flux divided by the surface area, so you would get flux density which is perpendicular to ds, or which is parallel to the direction of ds. Okay, so if you are using the same formula on the right hand side, flux divided by surface area, so you should know the component of the flux density which is perpendicular to this ds. So it means that we are interested in what? We are interested in, if I drop perpendicular from this head, arrowhead towards the direction of this patch surface, so this component is something which is ds normal. So if I want to use this expression, flux per unit area, I would get the component of the flux density which is normal to the patch, as was in this case. So where this delta psi is nothing but flux leaving this closed surface, so ds normal multiply by delta s, and this ds normal is nothing but ds cos theta delta s. So this is total the differential amount of flux leaving. So if we apply a limit that delta s tends to 0, this surface is so small that only one flux line is passing through it. And by the way, in that case I should write almost equals to. Why? Because we have considered this differential surface area to be very small, but larger than a point. So it might be possible that instead of one flux line, there are 2 or 3 or 4 flux lines crossing this incremental area. Okay, so we cannot make it exactly equals to. We should make it approximately equals to, and this would be exactly equals to if we apply a limit that delta s is so small that it is tending to 0. So I'm making this delta s to ds, and the rest is the same. So this incremental psi would become differential psi. So this is ds, vector ds, and this is a vector capital ds, and both have got an angle theta. So I can write it like this, that ds dot ds is equals to differential amount of flux leaving this differential amount of patch. So if I want to find the total flux which is leaving this whole surface area, what I would need to integrate this thing, which is ds dot ds, and this is integration with respect to surface. So surface has always 2 variables, so I would write surface, and just to emphasize that this is a closed surface, I would write it like this. So the flux in this arbitrary scenario where the charge distribution is arbitrary, where the enclosing surface is arbitrary, in that particular case, if you want to find the flux leaving or crossing this area, you will use this expression, and that flux which is actually crossing or leaving this area or passing this area, would be equals to charge enclosed by this area. Okay, so this is Gauss's law. This is Gauss's law. All right. So with this, I would like to stop here. But before stopping, I just want to give you one more thing, that this charge can be a point charge or it can be a collection of charges. So if it is a collection of charge, I would say that Q is all the charges summed together. Okay, Qm, where m runs from 1 to n. Okay, so this will give us total charge. And if it is a finite line charge or infinite line charge, whatever it may be, we know that charge is given by rho L dl. If the charge is a sheet of charge, so I can say that this charge can be represented as rho s ds. This is surface integral. And if this charge is a cluster of charges occupying some volume, which may be most of the case practically, in that case we can define rho v, volume charge density, for this sort of distribution. In that case, this charge can be calculated using this expression. So these expressions are something which you already know, we have already discussed about it. So most often case would be that this charge distribution is so arbitrary, so it is a cluster of charge. In that case, this expression will come out to be d dot ds, where the total charge is given by this expression. So rho v dv, volume and surface. So these two expressions, this is the generic expression, and this expression is most practical because this charge distribution practically would be in the form of a cluster of charges which would occupy some volume. So practically most probably you would be using this expression, but this is actually the expression of Gauss's law. So I hope that you would have understood the concept of Gauss's law. And one last thing, but a very important point, which I fear that if I won't discuss it here, I may forget it. When Faraday charged this inner sphere by positive charge, flux line started to leave, and they kept on continuing until and unless these flux lines found another metallic surface where they induced a negative amount of charge. So this gives us a clue. Whenever a flux line is given to you in some direction like this, so and you know nothing about the charge distribution, so you should remember that the tail point of that flux line must be originating this. If you keep on following this tail, where the tail starts, you would definitely find some plus charge here, and I'm talking about electrostatics. Okay, so you must find some plus charge here, and if you keep on following in this direction and try to find where this head of flux terminate, you will find that wherever it terminates there will be a negative charge. And this is the reason why, why we always show that the direction of electric field is for a negative charge is this. Why? Because if you put any judge charge around it, it will be in this direction, and if you have a positive charge here, so we always show the direction of the field in this direction. So whenever you put a judge charge anywhere surrounding this positive charge, it will be pushed in the direction of this field. And since we have found that direction of electric field intensity is same as direction of electric flux density, Only we have to multiply electric field intensity by a constant and you will get electric flux density. It means the direction is the same, so magnitude is different only. So it means that direction of flux is also the same for this positive charge, direction of flux is the same for this negative charge. So if you are given with a flux line like this, and if you try to trace the origin of this tail, you will definitely find a positive charge here, and you would definitely find a negative charge wherever this flux line terminates. So if there is no negative charge, then this flux line will keep on moving until infinity. Here what happened, this flux line found a metallic surface here, so it induced a negative charge on the inner surface of this sphere and got terminated there. Okay, had we charged this inner sphere by a negative charge, so we would have flux like this, flux direction like this, because there are negative charges here. So flux direction would be towards the inner sphere. So if you try to follow the tail of the this flux line, you would see there is a positive charge here. So had we charged the inner sphere by negative charge, the outer sphere would definitely, the inner surface of outer sphere would definitely have a positive charge, because at the tail of this flux line there would be a positive charge. At the tail of this flux line there would be a positive charge, same as the case of would be the case for all those flux lines. And if we had no outer sphere and only the inner sphere negatively charged, then these, if you try to figure out where this tail would end, that tail would end at infinity. So with this I would like to conclude today's session. Assalamu alaikum.